Good morning, everybody. I hope everybody is having a good start to their week, even though it's kind of rainy. I think it is warming up tomorrow and it's going to be sunny. So hopefully you guys are all doing well and you did your 6.5 homework. And now we're going to be doing 6.6, which is the last section of chapter 6. After this lesson, we are going to be recalling chapter 6, so I will be posting a practice assignment and a practice quiz as well. Okay, so our learning goal for today's lesson is we are going to analyze reaction mechanisms and determine if a given reaction mechanism is plausible for an overall chemical reaction. We're going to know the elementary steps that make up a chemical reaction. They have to combine to give the correct overall balanced equation. And the mechanism has to agree with the experimentally determined rate law equation. And then we're going to know that the slowest step in a reaction mechanism is the rate determining step. So again, this is all gibberish to you right now, but you can check back and see, yeah, I understand this after the lesson. So reaction mechanisms, what are they? If you tell a friend you are going from home to the concert, this just gives information about where you will be starting from and where you're ending up, but not how you are getting from the home to the concert. So let's say you had to walk a few blocks, take a bus, transfer to the subway, then walk a few more blocks. That's telling you the mechanism or the pathway of getting from your start to your finish. So like the trip from home to the concert, chemical reactions rarely occur in a single step. A reaction mechanism is a series of elementary steps by which a chemical reaction occurs. So what is an elementary step? It's the step involving a 1, 2, or 3 entity collision that cannot be explained by simpler terms. So an example. Here you have a chemical reaction, 4HBr plus O2 forms 2 waters plus 2Br2. It is highly unlikely that all 4 of these HBr are going to collide perfectly with this O2 at the same time and with the correct geometry to form the products all in one step. Okay, so the possibility of doing this is negligible. Okay, so instead, the reaction, like the pathway to get from the reactants to the products, happens in 3 steps, as shown here. Okay, so the first step is first one HBr molecule combines with one O2 to form this strange looking molecule, which ends up being an intermediate, which means it's not shown in the overall reaction. And this step is labeled as the slowest step, and we're gonna get to that in a second. And then the other 2 steps are fast. So notice when you add these 3 steps together, you use Hess's law to add them up, and you do get the overall reaction that we want. Okay, so again, this reaction is made up of 3 elementary steps. The slowest step in the reaction is called the rate determining step. The rate of the reaction can only be affected if the rate determining step is affected. So we'll talk about that in a second, but basically the rate of the overall reaction is determined by the rate determining step or the slowest step. Whatever is not shown in the overall reaction, which are HOOBr and HOBr, they're called reaction intermediates because they're produced in one step of the reaction and they're used up in the other step. So that's shown right here. So these are crossed out. This one and this one are crossed out, so it's called a reaction intermediate. Just a side note, as you're watching this lesson, you should be writing, have a notebook or some kind of paper at the side, because you should be writing down notes, especially when we get to the example, just as a like something where you can refer back to as you're doing your work for this section. Okay, so the rate law equation for the overall reaction is the rate law of the rate determining step, which is the slowest step in the reaction. Therefore, for a reaction mechanism to be plausible or possible, its rate law must match the experimentally determined rate law. And again, we'll go over this in the example. It'll make a lot more sense. Also, another requirement for a reaction mechanism to work is the elementary steps have to add up to get your overall reaction using Hess's law. Okay, so what is the rate determining step? So we're going to take a step back for a second to understand that concept. So one step in your reaction mechanism is always much slower than the others. So since it is much slower, it determines your whole overall rate of the overall reaction. So an analogy to this is making toast. So you cannot butter your toast until the bread comes out of the toaster. So if you had to write out, let's say we wanted to make buttered toast in the morning, if you wanted to write out this reaction in a series of steps, step 1 would be putting the bread into the toaster and your product is toasted bread. Step 2, which is the fast step, is putting the butter on the toast and you have your product here. Okay, so the whole overall rate of this reaction is determined by this slow step. This step determines how fast we will get our buttered toast. Okay, so here's another analogy here. Here you have sand going through this apparatus here, and our goal is to get all the sand to the bottom here. So the rate of this reaction is determined by the slowest step again. So the slowest step, so there's 1 step here, 2 step here, 3 step. Notice that these 2 openings are a lot bigger than this opening here. So therefore, this opening here is the slowest step and is the rate determining step. Okay, so this step right here determines how fast the overall reaction of the sand falling to the bottom is. Okay, example number 1. So these 2 examples I've taken in the PowerPoint are from your textbook, but I will be going over them on a piece of paper. So feel free, because in the next slide it says see document camera. So you are going to have to write down the answer to these 2 examples. So the balanced chemical equation for this reaction of nitrogen dioxide gas and fluorine gas is shown right here. So 2NO2 gas plus F2 gas forms 2NO2F gas. And then it shows you the rate law of the overall reaction right here, which was experimentally determined. And then they give you a suggested mechanism or series of steps to get to this overall reaction. So the question asks you, does this reaction satisfy the 2 requirements for a plausible reaction mechanism? So first of all, let's go over the 2 requirements to check if this reaction mechanism actually works. So the first requirement is, do these 2 steps add up to get to your overall reaction using Hess's law? So that's what we're going to start off first. Okay, and the second requirement is, does the experimentally determined rate law right here match our slowest step rate law? Okay, so it should match this step right here. Okay, so maybe take out a piece of paper and I will be transferring to the a piece of paper as well. Okay, so solution to example number 1. Step 1, do the 2 steps add up to the overall reaction? So what I did is I took the 2 steps that were given in the question and I simply added them up using Hess's law. Okay, so I added up all the reactants here. Okay, so NO2 plus NO2 gets me 2NO2, F2 plus F, and then I added up all the products. Okay, and notice with my red pen, I crossed off the ones that are in common, okay, and those are called reaction intermediates. Okay, and then I wrote the overall reaction here. Okay, so the overall reaction is matching the overall reaction from the PowerPoint that was given. So the first requirement is met. So I'm just going to stop here for a second so that you have a chance to copy this down. Okay, if you are not done, you can simply just pause the video and copy this down. Okay, step 2. Does the mechanism agree with the experimentally determined rate law equation, which must match the slowest step, which in this case is the first step? Okay, so if you look up here, this first step was given in the question as the slowest step. So what we're trying to figure out is, does the experimentally determined rate law equation that was given match that slowest step? So it must match. So if you look at the first step here, the rate law for this equation would be NO2 times F2, right? So if you go down, and the rate law for the slowest step does match the experimentally determined rate law from the note, which was given, KNO2 times F2, it does match it. Okay, so the rate law for the slowest step does match the experimentally determined rate law, hence the second requirement is met. Okay, and I encourage you to pause at this point if you want to write this down and process it a bit. But the last thing we're going to write down is, therefore, the reaction mechanism is plausible. Another word for plausible is possible. Okay? Okay, so we're going to go back to the screen for a sec. And we're now going to do another example. So here they gave you the rate law of a chemical reaction that was determined experimentally, and then they gave you some elementary steps, and then they said determine the overall equation, identify any intermediates, and determine the slowest step in this mechanism. Okay, so to figure out the overall equation of this reaction, you just simply have to add up the two steps here using Hess's law. Okay, and then whatever is crossed out, that's going to be our intermediates. And then our slowest step you can figure out because the rate law of that slowest step must match the overall rate law. Okay, so let's go through the solution. So the overall equation is you simply add the two steps that are given. Okay, so NO plus NO gets you 2NO plus NoCl2 plus Cl2. Okay, and you get that. And then notice NoCl2 crosses out with NoCl2. So that's our intermediate. And I just write my overall reaction right here. Okay, and I wrote my reaction intermediate is NoCl2. Again, if I am going too fast, just pause so that you can write it all down. Okay, so what is our slowest step in these two steps? How do we figure that out? So the slowest step must match the overall rate law that's given in the question. So the slowest step must be, let's go look at our question again. Our rate law is given right here. So our slowest step must have NO and Cl2 in the reactants. Okay, so let's take a look. Which step has NO and Cl2 in the reactants? The first step right here. Okay, so that is our slowest step. Okay? Okay, so after all of this talk about reaction mechanisms, why are they important? If chemists know reaction mechanisms in detail, they can develop techniques for controlling reaction rates and increasing the yield of desired products that can have industrial, environmental, and medical applications, because you can control how fast or slow each step is. So that's it for today's lesson. I want you to practice, hopefully, what we just discussed so that you can consolidate your learning. So try these textbook questions shown. If you don't have your textbook at home, I will post all of Chapter 6 on Google Classroom so you can access it. And if you have any questions about 6.5 and 6.6, I will be having a Zoom meeting tomorrow at 2 p.m. So make sure you check the invite on Google Classroom for that. And I will be posting as well a Chapter 6 assignment in the next couple days, as well as a practice quiz. Again, the assignment is not due as of yet. No assessments have been assigned yet. It's everything that we're doing so far is just learning. And hopefully building your foundation. And then once the board, I guess, decides what we're doing with assessment, we'll move forward from there. But for now, I just want you to kind of enjoy this journey of learning and building your foundation each day and keeping your brain occupied, because if you're doing nothing every day, it's not really good for you. Okay, again, if you have any questions or concerns, or you just want to check in, please join the Zoom meeting tomorrow at 2 p.m. and see you then. Bye.